So in section 2.4, we're going to take a closer look at the nuclei of atoms and have a look at the particles that make up the nucleus of all of our atoms. It's important to realize that atoms have no overall electrical charge. So for this reason, they contain the same number of protons, which are positively charged, as electrons, which are negatively charged. The number of protons that's found in the nucleus of an atom is called its atomic number. And we give the atomic number the abbreviation Z. So just recapping, the atomic number is the number of protons that's found in the nucleus of an atom. It's also the number of electrons, and we give it the abbreviation Z. Now, the atomic number is important is because every element has a unique atomic number. So for example, aluminum has atomic number 13, meaning that it has 13 protons in its nucleus, and then it also has 13 electrons. Iodine has atomic number 53, and so that tells us that it has 53 protons in its nucleus and 53 electrons outside the nucleus. As you'll see, every element has a unique atomic number. You may want to take note of this table in your book as it can be really helpful in answering questions later on. So this is an example exercise from our book, and the problem asks what is the number of protons in the nucleus of each element. So what we really need to do is we need to find the atomic number in each case. Now there are a couple of ways of doing this. You can look it up in the table that I showed you previously, or you can also look it up in the periodic table. And in the periodic table, you'll see two numbers. One is a whole number, and that is the atomic number. And then there's a number underneath which normally has 2 or 3 digits after the decimal point. That's not the atomic number. So for sodium, if I go to my periodic table, or I go to the table that I showed you previously, I see that the atomic number is 11. So that means that sodium has 11 protons in its nucleus. For oxygen, we can see from the periodic table, or from the table that I showed you earlier, that the atomic number is 8, and so that means there are 8 protons in the nucleus. For chlorine, if we look up the atomic number, we see that it is 17, and so that means there are 17 protons in the nucleus of a chlorine atom. Chem. The sum of the number of neutrons and protons in an atom is called its mass number, and the mass number is given the abbreviation uppercase A. So just recapping, the mass number is the number of protons plus the number of neutrons, which we abbreviate with the symbol uppercase A. Now, the number of protons in the nucleus is equal to the atomic number. The number of electrons in a neutral atom is also equal to the atomic number. And if we want to know the number of neutrons, it's pretty easy. We take the mass number and then we subtract from that the atomic number. So big number minus small number gives us the number of neutrons. So often we will provide the mass and atomic number of an element using the complete chemical symbol notation. And what we do is we write the mass number before and above the atom's element symbol, and then we write the atomic number before and below the element symbol, and then we write the element's symbol. So for example, this would indicate a hydrogen atom that has 1 proton, 1 electron, and then big number minus small number, 1 neutron. This would indicate a lithium atom that has atomic number 3, mass number 7, This would indicate a sodium atom that has atomic number 11, mass number 23. And this would indicate a gold atom that has atomic number 79 and mass number 197. So it might seem obvious, but when atoms interact, it must be through their outer surfaces. So when two atoms come together, they're going to interact via their electrons. And the number of electrons an atom has is determined by its atomic number. And so it's for this reason that atoms with the same atomic number have the same properties, because they interact with other atoms in the same way. So this exercise from the book is asking how many electrons are present in the atoms of each element. And remember that the atomic number will give us the number of electrons. So we just need to look up the atomic number either in the periodic table or in the table that I showed you previously. So the atomic number of magnesium is 12. Therefore, there are 12 electrons in a magnesium atom. I'm going to follow the same procedure for the other ones. Potassium has atomic number 19, therefore it has 19 electrons, and iodine has atomic number 53 according to the periodic table, therefore it has 53 electrons. And just remember, when you look in a periodic table, the whole number that's normally written above the element symbol gives you the atomic number. So neutrons, as we pointed out earlier, have no electrical charge. And for a given element, the number of neutrons might vary. So this is a modification of what Dalton was saying, where he said every atom of a given type has the same, exactly the same composition. We're saying, well, they have the same protons, they have the same electrons, but they might have different neutrons. So we have a special name for atoms that have the same number of protons, that is the same atomic number, but different numbers of neutrons, that is a different mass number. We call these guys isotopes. So for example, there are 3 naturally occurring isotopes of hydrogen. One has mass number 1, another has mass number 2, and the third has mass number 3. And keeping in mind that mass number minus atomic number equals the number of neutrons, our first isotope here has 0 neutrons, because 1 minus 1 is 0. Our second isotope here has 1 neutron, because 2 minus 1 is 1. And our third isotope here has 2 neutrons, because 3 minus 1 equals 2. They all have 1 proton, because they all have atomic number 1. They are different isotopes of hydrogen. So, looking at these a little bit closer, hydrogen 1,1 has 1 proton and 1 electron, and it has no neutrons in its nucleus. The mass number and the atomic number are the same. We tend to call this just regular old hydrogen. The isotope of hydrogen that has the symbol 2,1 hydrogen, this guy, has 1 proton and 1 neutron in its nucleus. That's why it's got a mass number of 2. And then it has 1 electron, which balances the charge of the 1 proton. The common name for this isotope is deuterium. The isotope of hydrogen that has mass number 3 and atomic number 1 this guy has 3 particles in total in its nucleus. That's why it has a mass number of 3. 2 of those are neutrons. 1 is a proton. And then to balance out the charge of the proton, it has 1 electron. And the common name for this isotope of hydrogen is tritium. But what's important is the outer surface of these atoms, what it interacts with other atoms, how it interacts with other atoms is the same. It just has 1 electron sitting in that orbit around the nucleus. So from the outside, all of these isotopes look the same as far as other atoms are concerned, and for that reason they behave chemically similarly. Now, something that's important to recognize is that most elements occur as a mixture of isotopes, but fortunately those isotopes are in fixed proportions. For example, hydrogen is a mixture of the 3 isotopes that we mentioned previously, but they're always in these proportions. Boron is a mixture of these 2 isotopes, but always in those proportions. And so on and so forth. Lithium is a mixture of 2 isotopes in these proportions. So it's not quite as bad as what one might think. There's not just like endless isotopes for every element. Okay, so breaking this down a little further, when we write the complete isotope notation for an element, before and above the element symbol, we write the mass number, which is the number of protons and the number of neutrons in the atom, and in particular in the nucleus of the atom. Below and before the element symbol, we write the atomic number, which is the number of protons in an atom. The atomic number is the whole number that is listed in the periodic table. We follow that up with the atomic symbol, which you can find in the periodic table. It's going to be either 1 or 2 characters. The first character is always uppercase, and if there is a second character, it will be lowercase. So here's an example for an isotope of carbon. The atomic number is 6, so therefore there are 6 protons and 6 electrons in this atom. And then the mass number is 12, so 12 minus 6 means that there are 6 neutrons in this atom. The neutrons and the protons are arranged in the nucleus, and then the electrons are at a great distance, orbiting the nucleus like planets around a star. So here's another problem from the book where we're asked to calculate the number of protons and the number of neutrons in each of the following. And we don't really need a periodic table for answering this. We just need to take note in each case of the atomic number and of the mass number. And then all we have to remember is that the atomic number is equal to the number of protons, and the mass number minus the atomic number will give me my number of neutrons. So if we keep those things in mind, it's pretty easy to solve these questions. So in the first case here, we have atomic number 79 for gold. So that indicates that we have 79 protons. And then in the second case for B, we have atomic number equals 11. So that means we have 11 protons for sodium. Ooh. In order to calculate the number of neutrons, we have to take the mass number and subtract the atomic number. And that means I have 118 neutrons for that particular isotope of gold. And then the same for sodium. And that means I have 12 neutrons for that particular isotope of sodium. So most folks don't have a lot of problems with a lot of difficulty with these kinds of problems. Something that's worth pointing out is that the atomic number is not always written, because as we have the symbol, we can always go ahead and get the atomic number from the periodic table. So you can see in this example, they've dropped the atomic number. You also will see isotopes written as the name of the element hyphen then the mass number. And again, if we have the name, we can get the symbol, and from the symbol we can get the atomic number. So a few variations that you might see, and hopefully they don't cause you too much confusion. Okay, and that concludes the section on the nuclei of atoms.